In this part of the presentation, we show explicitly the relation between activation energy and temperature. And the bottom line of this is how we can use rates of reaction as a function of temperature to determine activation energies. There's something called the Arrhenius relationship between activation energy and temperature. And in this K here is the rate constant. It could be a first order rate constant, second order rate constant. A is some constant representing is just some constant characteristic of the reaction, and this part is the rest of it that I'm trying to highlight here. This part is the exponential function, e to the minus EA, and the EA is this activation energy that we introduced before. R is the gas constant. It might be familiar from last semester, but this time it appears in energy units. The graph that I have here shows that the rate constant increases rapidly with temperature. And so that should be pretty obvious, and that's a characteristic of we get something that we can use to analyze if we take the Arrhenius equation and take the natural log of both sides. The natural log happens to be the inverse of the exponential function. And when I do that, I get this equation. Natural log K is equal to the natural log of A, that constant, minus EA, activation energy, over RT. If I look at this equation and I can see that it has the form of a straight line if K, the natural log of K, is the Y variable. Natural log A here is a constant, and 1 over T, 1 over absolute T, is the X variable. And then I can see that this has the form of a straight line. Y equals an intercept plus a slope times X. So if I plot ln K as the Y variable and 1 over T as the X variable, I should get a straight line. And the slope, and this is a mistake here, you should cross this off. The slope of the line is minus the activation energy over R. So this shows what the graph on the previous slide looks like when I transform it in that way. On this axis, on the y-axis, I have ln K, and on the x-axis, I have 1 over T. And notice I get a straight line. Now, what I can do is if I have a set of kinetic data, I can use any 2 points on this line, or maybe just not even make the plot, but just given 2 points, I can use it to calculate the slope in the usual way, delta y over delta x, and then from that slope, I can calculate the activation energy. That's summarized on this slide. So first of all, if I have a plot, it should be linear. The x-axis is 1 over t. Something that I can't emphasize strongly enough is that the temperature must be absolute. So I ordinarily am given this in degrees C. Don't forget to convert to Kelvin. On the y-axis, I have the natural log of K, where K is the rate constant measured at different temperatures. I find the slope of that line by doing a delta y over delta x. I can use 2 points to find the slope. There's one temperature and rate constant and another. So T1, K1, and it should say T2, another T2, and K2 here. And then the delta y is simply the difference of ln K2 and ln K1. And if I look at the properties of logs, I see that that is simply the natural log of their quotient. Remember, logs turn products into sums, and they turn quotients into differences. And so that's an important property of logs. And this is a little bit easier to compute, the natural log of K2 divided by K1. My delta x is simply 1 over the absolute temperature T2 minus 1 over the absolute temperature T1. And specifically, I warn you that this is not the correct way to calculate this. This gives you something completely different, something that perhaps that you should know from ordinary algebra, but is not equal to 1 over T2 minus 1 over T1. Please don't make that mistake. Okay, then with those two values, I calculate the slope, delta y over delta x. And then from that, I use this equation that the slope is equal to minus the activation energy over R, the gas constant in energy units, or the activation energy is equal to minus R times the slope. R is the gas constant and in energy units, which has this value in these units, 8.3145 joules per Kelvin per mole. When I carry out this calculation, I should get, and keep track of units, I should get joules per mole, and it's ordinarily expressed in kilojoules per mole. This slide shows an example, and this is similar to several mastering chemistry problems. So in this example, we say the reaction has a rate constant of 0.150 inverse seconds, and incidentally, this could be first order, second order. This particular example is first order, but I just compare the rate constants of two temperatures and the units cancel. So 0.150 inverse seconds at 20 degrees C and 4 inverse seconds at 49 degrees C. Notice how the reaction rate constant has increased quite a bit with temperature. The first point, K1, T1. K1 is 0.150 inverse seconds. T1, I have to convert that to absolute temperature by adding the 273.15, and I get 293.15 Kelvin. I do the same for the second point, which is the rate constant is 4 inverse seconds, and 49 degrees C corresponds to 322.15 Kelvin. I calculate the delta y, ln K2 over K1, which is 4 inverse seconds over 0.15 inverse seconds. Notice the units cancel. And I get, for my delta y, 3.283. And this has no units. My delta x, 1 over T2 minus 1 over T1, 1 over 322.15 Kelvin minus 1 over 293.15 Kelvin. I carry that out and I get the difference of these two small numbers with units of, careful track of units, inverse Kelvin. Take the difference and notice the difference is negative. T2 is greater than T1, therefore 1 over T2 is less than 1 over T1. So the difference is negative, and minus 0.0003071 inverse Kelvin. Now I use these two things to calculate the slope, which would be the delta y over delta x, and that I do on the next. The slope delta y over delta x has this value minus 10,692 Kelvin, so has the units of temperature. The activation energy is simply minus the slope times the gas constant, and so the negative signs cancel, leaving me with a positive number for the activation energy, as it must be, and I get 10,692 Kelvin times the gas constant in energy units, 8.3145 joules per Kelvin per mole. Notice that the Kelvin units cancel, leaving me joules per mole. And so I get this value, 88,902 joules per mole, and I express that in kilojoules per mole by dividing by 1,000. There are several examples like this in the Master in Chemistry, and it's the one somewhat involved calculation that I want you to be able to do.